Hi, I'm Steve Dodson, and I am going to introduce our next speaker. I know that Alan Ward is an amateur astronomer, amateur telescope maker that Russell Porter would have been very happy to know, and I think he'd be happy to introduce him himself, but he can't, so he's letting me do it. I've known Alan, and ever since he started his prolific telescope making career about 40 years ago. Several years before that, as a teen, he had become fascinated with the idea of making your own telescope when he read an article about telescope making in the Popular Science Encyclopedia. But one sentence in that article stopped him cold, spoiled his dream. It said, after you've done all the hard work and polished your mirror and figured it, you've got to send it away for a shiny coating. Fortunately, that shattered dream came back into focus when he met Sudbury's telescope pioneer, Ken Odaisky. Ken had made a gaggle of scopes, many with mirrors that he had silvered himself. With Ken's example, Alan quickly gained experience making telescopes, and he became a telescope mentor to many people visiting our local science center, Science North. Of course, eventually Alan realized that you could do away with the need to send your optic away as part of the process. All you had to do was make a lens instead of a mirror. So Alan's next telescope was a refractor. Now he makes world-class apochromatic refractors that have won a number of prizes here at Stellafane, starting in 2016. But Alan was far from done with mirrors. The next bold step was to renovate several old mirror coating machines, sort of like Stellafane is doing with this big coffee urn in the corner, which is a vacuum plant as well that needs to be renovated. And Alan became an expert in rebuilding coating machines and using them. And he developed the ability to set up a machine of that delicate nature in the field in 2003. Since then, he's refined his techniques for illuminizing telescope mirrors out in a camping field, which is really a major achievement, especially considering this equipment had to be transported about 600 miles one way. And, and Vermont is a crucial test of any portability techniques. Last time in 2019, he illuminized 15 mirrors made by convention goers and members of Springfield telescope makers. So there's no one better qualified to talk about mirror coatings than Alan, and here he is. Thank you, Alan.
Do I need this? Yeah. Thank you very much, everyone. It's great to be back, and right now we're coating our 6th mirror right now. Peter Pekar is at the coating machine keeping it running while I'm here. So I'm glad to be back, and it's really good to see everybody again. I recognize so many faces. I know I looked a little bit different 4 years ago. I'm the same guy. I'm going to talk a little bit about nothing. That's what a lot of this talk is about vacuum tech, a little bit about vacuum technology, which is the whole, your goal is to achieve nothing in the chamber, get everything out of there. And it's amazing what amateur telescope making will lead you into different technologies. And vacuum technology is a science in itself. So is thin films, which we're going to be talking about, optical coatings in general. This was back in 1993, where I acquired this dilapidated, unwanted piece of rust in Niagara, New York. And it was advertised in this kind of telescope magazine for $5,000 US, and I just grabbed it right away. And my friend, John Moon, was just shaking his head like this, like, don't do it, Al. Anyway, we dragged down a trailer, flatbed, and we pulled it back up, and I repaired it. So the question is, we have to drive this thing back through the border. And the first thing they're going to ask is, what's the rate of duty on rust? And what is this thing? It looks like a Frankenstein distillery or something. Copper tubing all over the place. Anyway, I was fortunate enough my brother-in-law was a customs officer at the border, so that helped a little bit. But mind you, we had to do the paperwork and do everything legit. But it just relieved a little bit of stress on my part. But bringing this little machine to the border was uneventful. Great. So I'm glad to be here with it. So anyway, I brought this thing in, and I needed, in order to build something like this or rebuild it, you need a lot of space. And I was fortunate enough to rent a building almost the size of this pavilion. And I tore it completely down and rebuilt it in about a year. And this is what it looked like about a year after. And I stripped everything right down to the frame. Every bolt, every wire was changed out. Every tubing was changed out. All the gauges were changed. It just served as a mechanical and electrical blueprint. And I just basically re-engineered it back together again. El Negro on the left there, this is my 6-inch f10 Apple. And I'm going to be talking about how oil space lenses work, okay? Not just coatings. And this was last time I was here with El Negro. Not El Negro, yes. And this, so before I got into coatings, Ken Odaisky was silvering my mirrors back in the 80s, but there was a place in southern Ontario, the David Dunlap Observatory, where they would illuminize their own telescope mirrors. And we go down there on an ad hoc basis and gather mirrors from northern Ontario, and I would do the yearly pilgrimage down there for many years to get a bunch of our mirrors done and then bring them back up to Sudbury. So I'm going to get into how optical coatings work, why do we use thin films for, and how we apply them on astronomical optics. So thin films can be used for many things. They can be used to reduce reflections off surfaces of lenses, as you know, and we can also use them to make mirrors very reflective. And they're also used to make deep sky filters, H-alpha filters, that sort of thing. That's all thin film sciences. So I'm going to digress a bit, because in order to explain how the coatings work, you need to use some physical analogies that you can observe in nature, such as when you throw a pebble in a pond, you see the waves go out in straight lines. So you may think that the wave is moving, the water is moving. It's not. It's the energy that's moving. The water is more or less staying where it is. It's just going up and down. It's the energy that's traveling. And this energy can travel quite fast, as you know, in a tsunami. It can travel as fast as a jet airliner, right? So that's very, very fast. So you can describe thin films, optical thin films, by using an analogy of an ocean liner. If you've ever seen an ocean liner in dry dock, you've noticed that they come with there's a bulbous bow in the lower front end of the hull. And what that does, so the main bow wave, right, creates a lot of drag on the ship, and it consumes a lot of fuel, obviously, right? How can we make this wave, less? If we make that bow wave a little bit less, we can conserve some fuel and energy. And they do that by introducing a second wave that's produced by the bulbous bow wave that you don't normally see because it's under the water. That's this thing here. It's kind of a protrusion in front of the ocean liner. So what happens is that you have the bow wave that creates a wave, but the bulb base also produces a wave. It's smaller, mind you, but it's a wave that's out of phase by 180 degrees with the bow wave. So here's the bow wave, and this is the bulbous bow wave. And as you can see, when you add waves together, they cancel out, or they can add together. In this case, they cancel out. So you get you almost save about 15% energy by introducing a bulb wave. So this is what we do with optics. We do the same thing. We either add waves in order to cancel them out, or we can add waves, multiple waves, and make them additive, so you get more reflections, or make them less reflective. Same thing with a skipping rope. As kids used to flip the skipping rope, and you'd see the wave invert and come back to you, right? So now you've got your degree in wave theory physics, so we can go ahead now and talk about how the coatings are done. So we've all seen uncoated lenses, right? You can see lots of glare off them, and They look kind of like foggy almost, right? Well, how do we get rid of that? Well, first of all, we need to know what happens to light when it enters into glass or any kind of different material or medium. And we get when light strikes a surface like glass, refractive index there is 1, and we're going to assume glass is 1.5. We're going to get about 4% reflection right off the bat from the light. And 96% of the energy will come through the glass, right? But it's going to reflect again, going out of the glass and into the air. And we're going to lose another 4%. But it's 4% of the remaining light that's going through, so that's why it's 3.8%. So that by the time the light comes out of that piece of glass that's uncoated, like a microscope slide or a lens that's uncoated on both sides, you're down to 92% efficiency. That's a lot of light loss, and if you can just imagine adding another lens behind that that's uncoated, now you're down to just, the reflections just, it gets really bad, right? We need to improve that. So how do we do that? Well, what we're going to do is we're going to add another layer of material on top of the lens. Here's a simple example of a single coating anti-reflective lens. And what they used to use in the day was magnesium fluoride. Now they use very multiple layer coatings. Magnesium fluoride just very easily describes how it works. So you notice that the magnesium fluoride has a much lower refractive index than glass does. So when that happens, we get less reflection off the air-to-air magnesium fluoride boundary. So it's only, instead of reflecting 4%, the magnesium fluoride boundary only reflects 2.5%. And then the rest of the light goes through the magnesium fluoride coating, but then it's going to hit now the glass. Whenever light travels from one medium into a different medium of different refractive indexes, you automatically get a reflection. That's just the law of nature, law of physics. So we're going to get another reflection, but you notice what's magical about this is that the light has to travel. I don't know if my laser's working. Yeah. The light has to travel a quarter wave. So this thickness is a quarter wave thick, about 100 nanometers. So the light has to travel through the glass, quarter wave, and out of the magnesium fluoride by another quarter wave. So it's out of phase by half a wave. So as you can see here, we get two reflections, 2.5% reflection, and another reflection here, and they both cancel each other out. So the resultant reflection is 1.4%, much better than 4% reflection, right? So now, 98.6 of the light goes through the glass, right? So it makes a huge difference. And then, of course, the same thing happens at the entry of the lens. The same thing happens. So this helps a lot, especially with a single lens and a double lens. For a Fraunhofer design, two lenses, it works great. There's not much light loss. You're still above 90% with four coatings on each lens surfaces. That helps a lot. But if you got like multiple, like in an Niagara eyepiece or something, you might have 9 elements in there, right? 18 surfaces or something. You need more coatings, multiple layer coatings than magnesium fluoride. So there's other coatings that you can put on top of this that increases reduce the reflectivity even more. You can get up to almost 99.9% or even close to 100%. And I've actually seen the technologies out there that actually make glass invisible. I've seen it. But they don't do it because of cosmetic concerns. It would be like you walking around with your glasses on with frames on only, because your glass would be invisible and you look kind of funny, right? So they actually purposely alter the coating so it gives a little bit of glare. Like sometimes it's magenta or green, right? But they can make the coatings so that the glass actually disappears. So the perfect scenario, we can have a perfect scenario here where the light has the same wavelength. Of course, we have different colors, right? So each color is going to react differently to the reflections, right? If they're the same amplitude and traveling the same direction, have the same point of origin, and they're all 180 degrees out of phase, then you have a perfect anti-reflective coating, but that doesn't happen in nature. That's why we have to use multiple layers. So this is an example of an optical hole. This is like, it wasn't coated with just half a quarter wave of magnesium fluoride. This was actually coated with many, many different layers of materials in order to get the optical hole effect. I made my own optical hole, square hole here. And you can see how much it reduces that glare off the light, right? Like off the glass, it makes a big difference. That's just I'm experimenting with just like, those frame glasses you buy at the dollar store. So let's get into aluminizing. So what we're doing up on the hill with the little machine is we're just putting bare aluminum on it. And what normally happens with this, like if you leave the aluminum coating on for a little time before you start using it, it'll develop a natural forming aluminum oxide layer, which is very, very strong, very, very tough, very, very hard film. However, it's very, very thin. It's only about 10 nanometers thick. But it's enough to give the coating a little bit of artificial self-protection. But it still doesn't have that strong durability. We need to make the coatings more durable so that they can last for many, many years. So we can improve the reflectivity of aluminum by adding dielectric materials to it. So this is how enhanced aluminum coatings work. We're going to so we have your telescope mirror down at the bottom here, right, uncoated. We're going to put 600 nanometers, or a tenth of a wavelength of light, thickness of aluminum on top of the glass, right? Now, the thing about aluminum, it absorbs some energy from light. It just does that. It absorbs 8% or so. Any light that hits it is going to absorb 8% of it. So we need to reduce that somehow. And by doing that, we're going to add layers to it. So we're going to add a layer, a quarter wave of magnesium fluoride on top of the aluminum, and then we're also going to add a quarter wave of cerium oxide on top of the magnesium fluoride boundary, and I'll explain how this is going to work. So cerium oxide has a very high index of refraction. It's 2.3, very, very dense material. So our light is coming in from the air, and it strikes the cerium oxide boundary, and because of the very high refractive index of the material, we're going to get a huge reflectivity off it, 34%. That's quite a bit. Okay? The rest of the light goes through the magnesium fluoride until it hits the magnesium fluoride boundary. And now it's going to reflect again because it's going from a medium of 2.3 into a medium of 1.38. So we're going to get a reflection going on here. And as you can see, it has to travel a quarter wave in and a quarter wave out. So now it's 180 degrees. So it's going to, but the thing is, it's going from a high index of refraction into a low-end refraction, so the reflections are flipped. And this is really neat how this works, because these two reflections are actually out of phase with the original light wave coming in. So these two reflections actually add together. Now, the rest of the light is going through the magnesium fluoride and it hits the aluminum finally. But we've already done almost 45% of reflecting before the light actually even hits the aluminum. That's quite magical. We want the aluminum to see very little light because it wants so much percentage on its own, right? It wants that 8%, right? But it doesn't have that 100% light hitting it at this point. It's only seeing maybe 50% of the original light. So it's going to steal only about 5%, or about just a little bit. We're going to get a reflection, but it's only going to be about 47%. And it's going to steal a little bit by about 5%. So if you add up all of these three reflections now from each one of these boundary layers, they're all in phase. And they all add up to about 95% efficiency. So that makes a huge difference. Okay, so now, because bare aluminum is 87% reflective. Once it comes out of the chamber, it's 92% in the chamber. Take it out in the air, it drops immediately down to 87%. So this is what happens if you got a Newtonian telescope. A single reflection off your primary is 87%. Off your diagonal, you're at 76%. So you're at 76% of the energy eventually coming to your eyepiece. So you almost got to get 25% loss of light immediately in a Newtonian using bare aluminum. Enhanced aluminum at 95%, two reflections will give you 90% efficiency. That's quite a bit more, right? Now silver, wow, look at this, 98% for a single one surface coating. With a 2 reflection system, we're down to 96%. Very high, very efficient. But we know the problems with silver, right? They tarnish, they turn brown, they turn yellow very quickly. You might get a year or 2 out of them. But if you do it yourself, which you can do now with new technologies, with spray silvering, which Peter Pecura did back in 2019, you can coat your own mirror for about $1 an inch in diameter. So that's going to be the way of the future. We're going to see amateurs doing their own silver spray coatings in the near future. Because this vacuum technology is just costing us a fortune to get mirrors coated. Now, if we refer to ball space lenses and some of the apochromats out there, same concept, what we're doing here. But we're using, instead of using a physical material like certain dioxide or magnesium fluoride, we're using oil. And if we choose an oil that has special properties, it does a lot of magic things for us. It can eliminate internal reflections. It can eliminate surface irregularities. So when you figure a lens, you don't need to figure the surfaces that are going to have oil in them. There's no need to do that. Some people don't even polish the internal surfaces if it's going to be oil-spaced. Isn't that amazing, eh? You can get almost, the lenses basically almost disappear when you use this oil. You can't see the interfaces. And I'll do an experiment here to prove it to you. So these are really wonderful lenses to work with. So in my Apo, I got 3 different types of glass. And so I need different types of oil in order to do the same effect. So you want the light to travel through the glass and out of the glass into the oil, and then into this glass, and out of this glass, into this oil, and then into this glass, without any absorption or any reflection. And you can do that by specifying the exact index of refraction that you want. And there's a lab in the States, I forget the name of it, it'll come to me, but they'll make you any oil to any specifications. And you take the average of the 2 glasses, and that's the oil for this separation, for this oil film. And then you choose this oil for this combination here. And it's the thickness oil is very, very thin. It's about 3 microns. There's very little oil that separates the lenses in this thing. Okay, so now we're going to do a little experiment here. I'm going to ask Matteo to come up. You can see this done online, but I like to do it in real life. And some of you may have seen this, not in 2019, but in 2018, I think it was. So it's called a disappearing beaker experiment. You can look it up online. So I got basically 2 beakers. I put the small beaker in the big beaker. You can all see both of them, right? What we're going to do now is Matteo's going to pour hopefully we'll have enough. I think we have enough oil. Check, look. Yeah, we're good. We'll use this one instead. Okay. Matteo's going to pour mineral oil. Okay. Mineral oil's got a refractive index very similar to Pyrex. He's going to pour it into the small beaker first and keep on pouring. Keep on going. Let it overflow. Keep it going. Okay, good, good. I can pass that around if you like. Just be very careful with it. Don't spill it.
I can see it. Just somewhere.
It's not a perfect oil for this scenario, but it works, right? And that's basically what we're doing.
That's just mineral oil?
Yeah. Yeah, it's not special. The special oils you get exact so that it completely disappears. Now getting back to the enhanced, this is an example of enhanced aluminum coating that I did at home. These are very durable. Here's a scouring pad. And I want you to rub this as hard as you can and try to remove the coating. I'll just pass that around as well. And this is just a quick glimpse of my shop at home here. I got grinding barrel, of course, the polishing machine on the left here, grinding machine as well. I meant the hot sauces and growing hot peppers, and optical test bench, and the coating machine in the back room. So this is how we do the coatings. Now, some of you have already seen how we do the coatings up on the hill there. This is my bigger machine, similar in size to this one. So the mirrors are mounted upside down, okay? And the fixtures, all the vapor sources are on the bottom. So we have the aluminum vapor source right here, which is a tungsten filament, and we load crimps of pure aluminum on top of that. And then we have a boat for whatever, sometimes we call it a spare, depending on what material we want to evaporate. Could be silver, it could be magnesium fluoride, could be anything, gold or whatever. And then we have another boats, such as silicon monoxide or cerium dioxide. So that's what the tungsten filament looks like. We have crimps that we load on that. So we put about 400 amps of current through this tungsten filament, and it glows red hot, white hot. It brings the temperature up to about 600 degrees, and the aluminum begins to melt. And at 600 Celsius, the temperature starts to go up again. And at 1200 degrees Celsius, the aluminum now boils off the coil because it's in a vacuum. And the vapor goes in all directions at about 1800 miles an hour. And that condenses on everything that it sees in its line of sight. So everything in the chamber gets coated, and the mirror, including your mirror. That's just an example of silicon monoxide. That's what we're doing, is silvering. We buy silver wafers at the bank. I don't know if I brought a sample here. Yeah, I got one right here. Silver ounce wafers here. You just cut them up with bolt cutters. Example of silicon monoxide. These are the two belts. So I put liners just like you do in an oven. It keeps the glass really clean all the time. Eventually, you got to change the layers out after maybe about 10 coatings or so, because they build up, and then the aluminum starts to flake off, and it creates a lot of dust and dirt inside. So you got to remove the liners frequently. I had some friends over years ago to see my machine. I was a chaperone for Thomas Bopp and David Levy one time when they came to Sudbury to give a talk at Science North. Here they are here in February 1997. Thomas Bopp has never seen snow before. And we had a big blizzard. And we had 7-foot snow banks. And we have this equipment in Sudbury that lifts the whole snow bank up and dumps it into a dump truck. He was just amazed by that. So that's us doing a 16-inch mirror. And then we do a glow discharge. It's hard to see in the tent because there's so much light going on, but maybe we'll do it tonight. So come around the tent tonight, and hopefully we'll do a glow discharge, and you'll be able to see the purple glow in the chamber. This is important because what it does, it removes adsorbed water that's in the chamber. So when we pump down, we're basically pumping out air and water vapor. But what's clinging behind are what's called adsorbed water molecules. Everything in this room, even though you think it's dry, has a film of water on it. And if you were to take a blowtorch to a piece of glass or a piece of metal, you'll see the moisture dissipate from it. And then when you remove the blowtorch, you see the water recondense on the surface. That's contamination. We got to remove that from the mirror, otherwise the glass, so that the coating can better stick to it. And so what we do is we bombard it with ions caused by the glow. So my big machine is at 15,000 volts, and it ionizes the residual atmosphere, basically water vapor and nitrogen, and it just basically molecularly sandblasts the surface of the glass, and it knocks off those adsorbed water molecules that are just stubborn things that want to stick to anything. So that eventually, we do that for like 15 or so minutes, and then we proceed down to high vacuum where we're ready to do the coating. So this is a schematic of the machine I have up on the hill. The big machine is similar to it, but it can do 2 chambers at the same time, or one can lag behind the other. Because I got 2 different mechanical pumps that I can use at the same time. So we get down to about a 1 millionth atmosphere pressure, which is very low. We don't call it, it's in millimeters of mercury, but we don't call it that, we call it torr. So you may have heard the terminology of torr when we're referring to vacuum technology. So we can get down to about 1 times 10 to the minus 5 millimeters of mercury, or torr. So it takes about, on my large machine, it takes me about an hour and a half or so to achieve that level. You don't need to get down that low for aluminum. Like up on the hill, we're doing it down at 4.3 times 10 to the minus 4 torr. And it works fine, even still at that vacuum. Now the diffusion pump, that's interesting how that works. Inside the diffusion pump, there's no moving parts. It's just basically a boiler of oil. So down in the bottom of this chimney here, we have a pool of oil, and we boil it under vacuum. And the oil travels up this chimney, or we call them shower heads. There's a 7-stack shower head here. And it's in a very high pressure vapor state. And there's nozzles here, similar to your shower nozzle at home. And what it does, it sprays out of there at supersonic speeds, and it's pointed downwards. So the oil vapor is basically pushing down. So if there's any air molecule that wanders into this pump, it's going to get pushed out, not sucked out. It actually pushes it can't escape. Just like when you turn your shower on at home, all the water that comes out of the shower head, it pushes the air down. So the air needs to go somewhere. Where does it go? Well, it goes underneath your shower curtain. That's where you can see it flutter sometimes when you turn the water on. Even though the water hasn't touched the shower curtain, you can see because the air is trying to escape. It can't go up. So it has to go down somewhere and escape out somewhere. So in a coating machine, it escapes out what we call the backing line. So the oil basically, it hits the sides of the wall in here, and there's cold water going through this all the time. So the hot water vapor, once it hits the inside of this chimney here, or the shower system, it's going to condense, and it rains down back into the pool of oil, and it recirculates. It gets reboiled, revaporized, recondenses, reboiled, and it keeps on going like that. And that's what brings it down to a high vacuum. As you can see, there's many parts to it. So it gets, when air, you can't have air ever seeing this oil vapor. Otherwise, you get soot build up on the aluminum. And it'll clog your nozzles eventually. You have to take the diffusion pump completely apart and clean it out. So that's what a 16-inch mirror looks like when it's done. Now what we do is, so you probably ask yourself, like, how do I know how thick the coating is and everything else? Well, we use interference. When you're applying the coatings, like the aluminum is done in a second. You just blast it away and it goes on. The other coatings, you can have control over it because it can take several minutes to do the magnesium fluoride and several minutes to do the cerium dioxide. You can take as long as you want, actually. But what you're looking for is looking at this. You're looking at the mirror at a very shallow angle, and you see it change colors on you depending on the thickness. So with magnesium fluoride, it'll start turning yellow, and then it'll go magenta. At that point, I stop it. That tells me I got a quarter wave on. Then I start the cerium dioxide coating. Then it's going to go from magenta, then it's going to go green. And then I wait for the green to disappear back to white, and I stop it. At that point, I'm done. So I can tell just by the interference colors on the mirror as to how thick the dielectric materials are on the mirror. Now I'll show you a picture of, that's not a good example there. I thought I had a better one. Okay, there it is there. So you can see the yellow here and the magenta. So the coating is not perfectly uniform. And the reason why is because the center of the mirror is closer to the vapor source than the edge of the mirror is, right? Because it's only 19 inches away. And the mirror is not curved like this. It's more or less flat, even though it does have a shallow curve on it. So there's going to be always a hot spot on the mirror and a weak spot. So what you want to do is, seeing that there's a diagonal in the way anyway, You make the hot spot to be the center zone because it's going to be covered by your diagonal anyway. So you overcorrect the center zone, which I've done here, okay? And what you do is you optimize the 70% zone to be the optimum zone. That'll be a mirror. That divides your mirror area in half. And so now you got more of a uniform coating. The 16 inches are really hard to do because it's a larger mirror. The smaller the mirror is, the more uniform the coating will be. Otherwise, you have to get a really tall chamber. So the taller chamber you have, the better, the more uniform your coating can be. But I'm limited because I got, on this machine here, the dome is much more shallower, so you can probably mount your substrate or your mirror a lot higher in this machine than I can in mine, because mine's dome-shaped. So my bell jar closes in very quickly, so I can only mount it so high. And then we bake the coatings in an oven that's never seen any food before. We bake it about 250 Celsius. And what that does, it cures the coatings. The dielectrics need to be heated, so they get really, really hard. And so we let it cool off very slowly overnight. And this was the first coating we did here at Stellafane back in 2019. This is a club member that we did a coating, and there's the glow. That's pretty much the talk. If anybody has any questions? Yeah, we're over here.
Would you speak to the value of coatings on glasses when you go to an optometrist? Like, for example, they have a no-glare coating. What are your thoughts on the coatings that go on lenses that people wear on glasses?
Well, I was just there last year, and I was very disappointed to find out that in Canada anyway, or in Sudbury, you can't get real glass lenses anymore. It's all plastic. And I'll guarantee you this, when I had real glass lenses for my glasses, the coatings would last almost forever. I got glasses going back to the 90s that are still perfect condition. These are plastic, and the coatings are already rubbing off on them. Because the coatings don't stick as well. They're not as durable as they are on glass. You know why? Because they're baked. These are not baked, otherwise the plastic would just melt, right? So they're basically at room temperature. So yeah, and as for the coating, I was able, back in the old days, you were able to be able to specify what kind of coating you wanted. You want green or magenta, but they won't do, optical holes because they don't sell that, even though they can do it. Yeah, we're here.
I have a 6-inch refractor that has oil-spaced objective. Is there any special handling that you should use versus air-spaced conditioner? I'm just wondering to maintain those oil-spaced in the objective.
There's, I've never had, I've oiled my lenses back in 2016. They're perfectly fine. They've seen minus 40-degree weather, Celsius, and that's the same as Fahrenheit. They've seen extreme heat. They've been used, again, they've been used pointing at the sun, using a Herschel wedge for many hours. I've never had any bubbles or anything like that form. They should, over time, I'd imagine that, sometimes you might have the oil leak out because they use Kapton tape to seal the oil, right? I thought I had some Kapton tape here. The lenses are sealed on the side with Kapton tape, and that prevents the oil from not so much leaking out, but it prevents it from evaporating out. Yeah, kind of, yeah. And you want to make sure that your cell, like I left 25 thou. My cell is 25 thou larger inner diameter than my lenses are in order to control contraction in the wintertime. Because I've measured my cell, I put it in a deep freezer after it was machined, and it's amazing how smaller, the size of it really diminishes by several thousandths of an inch in a deep freeze. So you don't want that pressure going against your lenses, right? So you want to make sure that in very cold weather, you don't want your lenses to be, touching the cell. Oh yeah, yeah. Hey, up.
I saw a discussion of oiling lenses in which somebody said that when the lens radii don't match closely enough,
Yeah.
the oil can be too thick.
Yeah, very good. Yeah, very good question.
But I had
Yeah.
another point, and that is that vacuum down, there comes a point when just because of the vacuum,
It disappears.
it disappears.
That's what it does out there. That's what I use that's what it tells me.
Do you know,
Yeah.
do you know or remember at what pressure the discharge is?
Yeah, 1.3 times 10 to the minus 3 torr.
So it's still not quite good enough to do a little.
No, it just gets you into the, yeah.
It's the beginning of the high vacuum, but not quite good enough.
Yeah, actually, we can probably, you know something? We can probably get an exact reading for you tonight or the next time we do a coating. I'll be more cognizant with that, and I'll see what the vacuum gauge is actually reading when the glow actually disappears. That's a good point, yeah. Yep. Yeah, go ahead, yeah.
This goes back to but I silvered my first mirror, but a little effort didn't last all that long. So the next thing I did was I sent it off to the aluminum. And at the time, one of the only people doing that was Dudley Leroy Clausing. And he marketed his coating as Beryllium, B-E-R.
Yeah, it's a beryllium aluminum alloy.
Is that really a different alloy? Or
Yeah,
it's marketing?
no, apparently it's beryllium and aluminum alloy, yeah. Yeah. No, I've just heard about it. I remember him offering the services back, it was C.A. Clausing or something? Yeah.
Dudley Leroy.
Oh, yeah, right. I remember, yeah. Oh, right, yeah. Yeah. Yeah, what the coating was like there was a company, right, that you just mentioned that they were advertising a BEAL. Yeah, so like what did that represent? So it's basically a beryllium aluminum alloy. I've never seen it. I've heard about the coatings. I've heard of other people using its coatings, but I've never seen it actually. I don't know if there's claims to be a little bit more reflective. It could be more durable. I think it was maybe more durable because aluminum is very soft, right? And yeah, so it could have been just a hybrid coating where it may be a little bit more durable than bare aluminum, but I don't know how the reflectivity would be.
And beryllium is extremely poisonous.
Yeah.
Not something you want to mess with.
Oh, really?
You wouldn't want to take it off yourself. You wouldn't want to take it off, and you wouldn't want to even handle it any time you divided the format.
Yeah. And back to Rick's question about the radiuses of the lenses, right? If the radiuses have to be perfectly matched, because if they're not perfectly matched, you'll get bubbles or air spaces because the coating is so thin, right? And it's really, really thin. So, and that's the thing, you can't grind, when you're grinding lenses out of the same radiuses, you can't grind them together. I always thought that. You can just grind the two of them together and assume that they're going to end up being the same. They're not, because you have that interface between it. You got that grit layer between it. You have to use separate tools to grind these radiuses separately. They can't be, those glasses can never touch each other until they're oil spaced together. So you need a very high-end, accurate spherometer down to 1 micron. That measures Sagitta in 1 micron. Okay, so all my lenses are done to at least 1 micron tolerance in Sagitta, or across a 6-inch diameter. And only then will you ensure that the oil will be applied properly, because otherwise you'll see the air bubbles. I was told that by Roger Cherajoli, that make sure those radiuses are exact, otherwise you'll have problems with your oiling.
You mentioned the spray aluminum process.
Yeah.
Does it work?
Oh yeah, Peter's the guy to talk to. He gave a talk in 2019. He actually did a demo here, and he silvered Dave Kelly's 12.5 inch. It was quite a success. So you can do this yourself. You can buy the kit for, basically it works out like about $100 or so, but you can do like 5 20-inch mirrors for about $100. And it's just done with, you buy these chemicals, and you have 2 spray bottles, and use distilled water and calcium carbonate to clean the mirrors off really well. So a very vigorous cleaning exercise, right? And lots of water is used, distilled water. Everything's got to be kept wet all the time. You can't let the mirror dry off at all, otherwise it won't work. But there's a lot of videos, like we've done some videos on YouTube. You can see the whole process, but if you really want to know more about the spray silvering process, talk to Peter. up at the coating tent. He'll tell you all about it, how to get into it, which company to buy the chemicals from and everything. He's he was part of that whole team effort that basically worked together to make this all happen. So amateurs can actually spray coat their own mirrors. Yeah.
If silver is so great at reflectivity, why hasn't somebody figured out a way to coat it in such a way that
Yeah. There is proprietary secrets to that, and I haven't figured it out myself. But it's a how much time do we have? Almost done. Yeah, it's I think they're using silicon dioxide or titanium dioxide on top. The problem with silver is it doesn't like to stick to nothing. That's its problem. It doesn't have a really good cementing. It doesn't adhere to anything very well. It's a noble metal, yeah. It doesn't like to be friends with anybody, right? So it's not mechanically durable, yeah. And of course it's sulfur, and it doesn't like sulfur, right? Or it loves sulfur, but we don't like sulfur. Yeah.
I did it myself a number of years ago, and there's a tin mordant that you're supposed to coat it with. Yeah. It's just
What did he? What did?
the silver stick there.
Stannous chloride or something?
Oh yeah, it's a tin. That's part of the spray silvering. There's a solution of tin oxide, or it's in a stannous chloride solution, I believe, and you pour that on the glass first, and that because silver likes tin, right? So it gives a little bit of a bonding layer, a little bit better.
That's something they sprayed on it afterwards, right? It was supposed to coat it and make it more durable or
Yeah,
less
yeah, yeah.
And I didn't know, that's what I meant. I didn't know what the final surface turns out to be.
Right. Yeah. Question over here.
I'm just trying to answer the question of the heat for housing.
Oh.
His son took over the business. It's a very small shop. They don't advertise to amateurs, and they're still in business. Give them a call. They're available on the internet.
Is it still barrel?
Yep. Now, they do have a whole bunch of other coatings. You can have the barrel one is the inexpensive one. So there's no, I don't think there's any over coating. I think and I've used it for years. It's a durable, a very durable coating. If you want the super, you can't 92%. He'll do that for you for about twice the price.
Yep. Okay.
Yeah. Yep.
Leroy coated my 6-inch first mirror in 1954.
Really?
And charged me $3.50. Wow. I wonder what Dudley will charge me today. I need to coat the mirror again.
Oh, really? Now it's that old. Wow. That's amazing. I actually, I had some celebrity mirrors come to through my shop once. One of them was made by Textro, believe it or not. Yeah. Interesting. So I think I'm pretty much done here, folks. Anyway, any more questions, I'll be free to answer anything more. I'll be back at the tent there, so thank you very much.